Hello and welcome back to Learn It from a Layman. I'm Carl Christensen, joined today by Cameron. It's been a while.
Hey.
Well, nice to have you back.
Yes, the absent man who is coming back
Yeah,
to
yeah,
revel in our random knowledge.
that's right. That's right, and contribute there too. Okay, awesome. We have Cameron back and Matt, who's going to be regaling us today with the basics of rocket science, which parenthetically, we've kind of done different parts of it before, but Matt's got some additional insight and kind of a new way to view it for us. And so I think this should be pretty awesome. Additionally, rocket science sounds awesome. So, Matt, what do we got?
Because who doesn't love it? Okay, so first off, I hope that you've all done your prerequisite listening to the basics of orbital mechanics, which, no kidding, is a thing that we did, and it was reasonably accurate in its content. So you should all definitely go listen to it.
That's tagline for the podcast: reasonably accurate in the content.
Yeah, I mean, there's standards, and then there's standards. So, yeah, orbital mechanics, when we did that one, was one of our more scientifically truthful ones. So, yeah.
Yes, it was good. It was very good.
Yep. But that one had to do more with, the basics of space once you're in space. When we talk rocket science, we're going to be talking about the basics of get yourself to space. Space before space. That makes
space
sense.
Before space.
Yeah, we're talking rockets. The things that get you to space.
Yeah.
All right. So anyway, rocket science is how you get up to space and how it controls all of the motion once you're actually up there, and how you will move around within the orbits. But with any of these space things, remember that orbits all deal with ellipses and circles. Okay, not circles, just ellipses, But that's kind of going to be beyond what we talked about today. So I'm just going to be talking about rockets.
Awesome.
So anyway, you may have thought to yourself, what is a rocket? So I'm just going to ask that question. What's a rocket?
It's that pointy cone thing that you shoot off as a kid with the with the like hobby store engine inside that like comes back down to ground with a parachute and usually gets lost.
Right. Okay. So many of you have dealt with a rocket as a child. But what is it that makes that little toy a toy rocket versus a toy, toy?
Cameron?
What is the characteristic of rocketry-ness? Basically, what defines a rocket?
I'm going to say the type of fuel that you use.
Okay, fuel can play as part of it.
I like that.
The shape of your projectile?
A little bit less.
No?
It really does.
Arrows are called missiles.
It really does have to
rockets.
do with the fuel and the method of propellant, and it's basically using a jet of mass to provide propulsion. And I'm going to cite everybody back to another of our previous podcasts that they now need to go listen to. If you listen to our Basics of Physics podcast, where we talk about Newton's laws of motion, one of those laws of motion is essentially every action has an equal and opposite reaction. And a rocket makes use of that by spitting out mass from one end at a high speed that produces a motive force on the body in the other direction. So, rocket, a device that uses stream of mass to provide thrust or propulsion.
Nice.
Specifically, when we talk about rockets, we're talking about things that use a finite amount of basically all of the products involved in the rocket reaction and in the thrust reaction are contained in the rocket, as opposed to a jet engine. A jet engine uses a whole bunch of air that it slurps in, and then it essentially smushes that air down, compresses it, then sets that compressed air on fire and spits it out the back. Now, the fuel that a jet engine uses to do all of that is contained in the vehicle, but it makes use of a constant stream of incoming air. Rocket doesn't do that. A rocket uses whatever propellant it uses in whatever reaction it uses that propellant. But all of the things that make that reaction happen are contained within the vehicle from the beginning. So that's kind of one of the differences between, a rocket and a jet. Those get mixed up sometimes.
Okay,
Okay.
and maybe you'll talk about. Oh, go ahead, Cameron.
Oh,
I might,
I was
but I
gonna
might
say,
not.
so let's say a thruster on the International Space Station.
Yep.
Would that be considered a rocket?
Yeah, almost any kind of propulsive device in space is going to be rocket based,
But-
because there's no external things to ingest like
We
air.
bring up fuel to restock that, right?
Yeah, we do. But the actual, when the reactions happen and that thruster is activated, it's using fuel that is in the tank.
Okay.
In that sense.
All right.
And it doesn't use any kind of external material or matter like, air. So,
Would you
Okay.
suggest that we watch October Sky
no, I
for
wouldn't.
a layman view of how rocketry is?
No,
No?
that's the layman view of how a bunch of plucky young students can make something happen, but it doesn't go into what rocketry is at all. For that, be serious, you need podcasts,
Rocket Man.
which is why we
Oh.
have Learn It From a
Oh
Layman.
yeah,
You're
Rocket
welcome.
Man. How did I forget Rocket Man? I
Yeah.
mean, the dude puts a rocket pack on his back and can fly.
Documentary. Okay, so rocket fuel. That was going to be my question.
Yep.
Maybe you're going to talk about rocket fuel, but I was wondering about the composition versus your traditional, what the layman has experience with as far as fill up at the pump type of fuel.
You're wondering a little bit ahead of yourself there. We'll get into some of the
okay.
types of fuels and things in a second. So
Cool.
But anyway, all right, let's talk about how rockets work though. The big thing we're going to talk about is the aptly named rocket equation. I mean, that's what it is. And it's an equation that talks about how much oomph, that's a technical term, you can get out of any given rocket or any given fuel, vehicle, whatever. Let's talk about what I mean by oomph, because that actually matters. Things as they fly around in the atmosphere on their way to orbit or even in orbit, how do we measure how quickly they're going somewhere? What's the term that we use to quantify that?
Velocity.
It is velocity. What's the difference between velocity and speed?
Momentum.
But no.
I don't know. I was just
That
naming
was a
some.
great layman guess.
I was going with a physics term. Okay.
Well, you just throw out random physics terms when in doubt.
Yes. Exactly.
Velocity is the rate
Friction.
of speed over time.
No, it's absolutely not that. But
Which
Mass.
one, Carl or me?
yeah,
Both of us were wrong. Oh, okay.
yes, you were. I'm sorry. Unless, actually, I didn't really listen to what you were saying. I just didn't hear what I wanted to hear, so I assumed it was wrong.
I said velocity is the rate of speed over time.
No, it's just speed plus direction. That's the difference.
Oh.
Mm.
Velocity
That's a
is
vector.
a vector that has a directional component to it. So if I say 20 miles per hour, I'm talking about a speed. If I'm saying 20 miles per hour north, I'm now talking about a velocity. And that's kind of critical because the way that the rocket equation works is it quantifies a change in velocity. And this is important because everything that you do in orbit has to do with changing your velocity, changing it from being no velocity to being a velocity in a certain direction that is going quickly enough that you can escape the gravity or do whatever it is that you're supposed to be doing. Resist the um, perturbations in gravity that would deorbit your satellite or that would pull you into the sun or any of those other things. All of those, anytime we deal with space and rockets, we're dealing with a body that's being operated on by a whole bunch of different forces. And in order to resist those forces and go where you want to go, you're going to need to apply a change to what your velocity would otherwise be. And the change in velocity is represented by the term for change, delta, and the letter abbreviation for velocity, v. So the change in velocity that we deal with in the rocket equation is represented by delta v. And you will hear that all over the place when you deal with space and rockets. And I'm going to use it for the remainder of this podcast because I assume that you understood it all and that there will be no further questions about what I mean by delta V, right?
Yeah, I mean, all the time I'm walking around, I hear people shouting Delta V.
Yep.
Yeah,
and
I mean,
when you're walking around,
Most of the
the
time,
instant you
I hear
change
that
direction, you
called
have changed
campus
your velocity. And you
Delta
exert some
pi,
delta
delta
V on
V.
yourself. Yeah.
Delta.
The airlines. Anyway.
Delta
okay.
Sigma Chi.
So
Yes.
consider.
Okay. Never mind. We're good. Continue.
So let's talk about a couple examples of where you would want to apply delta V. The first and obvious one is when you're a rocket sitting on a launch pad and your velocity is 0. You want to go from having a velocity of 0 in no direction because you're not moving to having a velocity that is big, going generally up-ish. And in order to do that, you need to apply that delta V. Well, how much delta V do you need and how much can you get from your rocket? That's what you get from the rocket equation. And so that's example 1. Example 2 would be you're already in space and you now want to change your direction. Now, as we know, space goes in circles, right?
Yeah.
I think it depends who you listen to. Some people say it's linear.
Well, it's ellipses. I keep mixing that up.
That's an egg. That's not a circle.
Anyway.
Okay.
Imagine that you're an airplane and you're flying west at Mach 1. Now, you want to turn and go north, also at Mach 1. What is the delta V that is required there?
Mach 2.
Actually, yeah, it is. It's Mach 2.
Yes.
And the reason is you need to stop your Mach 1 velocity going west, and you need to generate a Mach 1 velocity going north. Now, with an airplane, does it really take like twice the amount of fuel does it take that much fuel to actually turn 90 degrees?
No.
No, it doesn't. And that's because an airplane has, wings and its control surfaces can make use of the forces of the atmosphere, lift and drag and so forth, to execute that turn. What if you're a rocket, though, and you're flying around in the void of space and you're headed in some direction and you really want to be headed 90 degrees some other direction? Well, that's where your delta V demands become as heavy as they are. And they are that heavy because you don't have the atmospheric forces, the lift, the drag, the control surfaces, the wings to play with the same way when you're in space. And so instead of being able to just turn, you you have to use thrust, a thruster, a rocket engine, a motor, a nozzle, something. You have to put that delta V out there.
Is that like the Wall-E movie, right? When he has the fire extinguisher?
Yeah, because that's scientifically accurate. But yes, the
Seems
fire
like it.
extinguisher provided a change in velocity to Wall-E, and there you go.
I mean, there's a vacuum inside the fire extinguisher while he's in a vacuum. I think it works.
Yeah, and I think when he was saying Wall-E, what he was actually saying is delta V.
I'm pretty sure that's not it.
Well, I mean, maybe. Go back and listen nice and close. Okay.
I'm almost certain that's not it.
Yeah, well, maybe. Okay. I have another question. I don't know where you're going now, but I have a question about a rocket launch I saw a couple nights ago. So
Okay.
when you have time.
Excuse me. Yeah, we'll come to that in a moment.
Okay.
All right, let's talk about the rocket equation. The rocket equation is, I mean, you do this with a calculator, but it doesn't have that many terms in it. That said, it's important to understand what all of these things are. And the rocket equation says that the change in velocity is equal to the specific impulse of your thruster times the gravitational acceleration of wherever you are on the face of the Earth. That would be 9.81 meters per second squared down, times the natural log of the total mass of your rocket divided by the mass of your rocket minus propellant. And that mass ratio, the total mass divided by the mass without propellant, I mean, well, it is a mass ratio. And that's the standard for any launch vehicle. If you think of some of the big rockets like the SpaceX Falcon 9 or the Starship or the Delta Fours or whatever, they're these big, giant, chunky vehicles. And then when empty, they weigh a certain amount. And when loaded up with fuel, they weigh a certain amount. Again, acknowledging that weight and mass are not the same thing, but you add all of that mass of fuel to it. So if you have that ratio and you take the natural log of it, you multiply that times the gravity of where you are and the specific impulse of your propellant, you get the maximum amount of delta V that you can get out of your vehicle. And so for something like a Falcon 9, you need a delta V that is pretty huge. You need to be able to change the velocity of that thing from 0 to going, Mach 18 or something in the direction of generally up. It's not up, but you know what I mean. And so that takes a lot of propellant and a lot of energy and stuff. How much energy, how much propellant? Well, it comes down to the rocket equation. Based on what you're doing, you can figure out how much delta V that you need to complete whatever orbital maneuver it is. If you need to simply speed your orbit up a little bit, make it bigger, that's a small amount of delta V. If you need to change your orbit to a different inclination, maybe you're going around the equator and you'd really rather go around the poles. Well, see our orbital mechanics podcast, but that is a huge amount of delta V. You can figure that out. If you're trying to launch, that is a certain amount of delta V, a certain amount of change in the velocity. Once you know how much delta V you need, you can then figure out characteristics of your rocket, like how big it needs to be and how efficient of a fuel source it needs to have. The how big it needs to be comes into that mass ratio. Generally, you'll be able to determine how much fuel you're going to need versus how much other mass, the structure of the rocket, the payload, the control systems, and so on and so forth. The specific impulse that I mentioned, that's going to be a function of what fuel you choose, and I'll talk about that in a little bit. But assuming that you know your delta V requirement, you know the change in velocity that you need to do whatever it is that you're doing, assuming that you know what fuel you're going to use, and assuming that you know the gravitational constant where you are, whether that's in orbit or on the surface of the Earth, then you can, the last remaining term in the rocket equation is that mass ratio, the natural log of your initial, your initial total mass versus your final mass after your propellant has been expended for that maneuver. Or if you want to know the total delta V of your rocket, the final mass with no propellant. And so you can figure out what that mass ratio needs to look like. And usually when we're dealing with rockets, the mass ratios are pretty heavily slated toward you need a ton of fuel. Along the lines of 90% of the mass of your rocket is going to be fuel of some sort, whether it's solid fuel or liquid fuel or cold gas fuel, whatever. Much of that mass, in order to do the things that you need to do to get something into orbit or to keep it in orbit, is going to need to be fuel. And so that's what rockets are. They're giant fuel tanks at the end of the day. Any questions about that so far?
No, but both of the questions I have do relate to some of the stuff you were just talking about in the practical application of launching a rocket, but not specifically about what you were just saying.
Okay, well, let's see if I come to them as we go forward.
Okay.
I probably won't, but then we'll come back to those. Okay. All right, let's talk about the specific impulse. Specific impulse is a fun parameter to try to explain. But it's basically how much thrust you can get out of a certain unit mass of your thing. It's measured in oomph per kilogram. You could think of it that way. You shouldn't think of it that way. If you're an actual scientist or engineer and you're hearing me describe it like that, well, I'm sorry, I'm layman stuff, whatever. But when different types of fuels will have different specific impulses. And since we're going to go deep into the dark magic, we'll give you the equation for specific impulse. Specific impulse equals a proportionality constant, K, and that's the thing, look it up, times the square root of the heating, it's the chamber temperature that your combustion or reaction is happening in, divided by the molecular weight of the exhaust, whatever exhaust is coming out of your thing. So things that make you have a high specific impulse, super high temperature. The higher your temperature, the more specific impulse you can get and the more efficient your engine, your rocket will be. So you want things that burn really, really hot. The other thing that makes your specific impulse high is very low molecular weight of the exhaust. So if you have something that burns down into things like hydrogen, oxygen, very light elements, that works well too. That's why liquid oxygen is such a useful rocket fuel. It burns very hot, and the molecular weight of the exhaust gases, often water, is relatively low. So all of these different fuels that are out there, and there are 3 different types, and we'll talk about them. They all have different specific impulses that go with them. And you might think to yourself, well, I'll just choose the fuel that has the highest specific impulse. Well, okay, but all of these fuel types have different trade-offs. A very high specific impulse fuel, like a Hall thruster, might not really be scalable to the point where you can use it to heft a giant rocket into space. Might be great for doing something like station keeping on orbit, where you can the actual force that you need to exert is very small, and you need a very efficient thruster that can last for 20 years. But to scale that to actually launch a satellite and apply enough delta V to get it into orbit may not be practical. Well, what if I use some other type of thing? Solid fuel motor. Well, that's cool. That has a pretty high specific impulse, but there's usually no way to apply a throttle control to a solid fuel motor. Solid fuel rocket motor is a rocket motor that uses solid fuel, shockingly enough. When you set it on fire, it just burns and it does not stop burning. And you can't really, save for a couple design considerations that I'm not going to talk about, notching, you can't really control the rate at which it's going to burn. It will burn at the rate that it burns, and you're going to deal with it. So that's one of the considerations. Do you need to be able to throttle your rocket motor for whatever application you're doing? In a heavy lift launch vehicle, maybe you don't, maybe you do. So solid fuel has its place. Liquid fuel also has its place. Different liquid fuels have different specific impulses that come with different trade-offs. Some high impulse liquid fuels are really efficient and deadly toxic. So maybe we don't use them for all applications. Maybe sometimes it's worth it, and so you do. But there's all these different trade-offs, and fundamentally at the end of the day, you want to find the thing that will give you the appropriate specific impulse, the appropriate efficiency to do whatever your application is. And based on that, you're going to have to size the rest of your rocket accordingly. If I have a low specific impulse fuel, I'm going to probably need more fuel or a higher proportion of fuel in my overall mass. If I have a really efficient fuel type that is a very high specific impulse, then maybe I can get away with more payload and more structure and more other stuff and less fuel as a proportion of my overall mass. And again, things that I'm looking for if I'm trying to develop a new fuel that will give me a high specific impulse, I want something that burns hot and breaks down into low molecular weight exhaust. So that's specific impulse. And then once I have that, and once I know the mass of my rocket, both with propellant and once my propellant is burned up, then I know how much delta V I can get out of that thing. And when I know how much delta V I can get out of it, then I know what I can do with my rocket, and I know whether it's enough for my application. So any questions about that? Rocket science is really quite easy.
That actually does make sense why we don't use radioactive material for rockets, actually. So,
well, or at least we don't use them in places where that material can come back down to Earth and be a problem.
But they don't break down to lightweight things, right?
Well, that's true. Yeah,
material are generally on the higher side. So
yeah, you don't generally use heavy elements. Solid fuel rocket motors, I mean, essentially it's rubber. It's a lot of rubber that you set on fire. It's often not super clean, but it does break down, and you can pack enough of it, enough mass into a rocket, and it burns hot enough that it will often do the job of hefting something into orbit. Now, solid fuel rocket motors would be terrible to use on orbit for something like station keeping, because again, it's either on or it's not on, and once it's on, it doesn't stop. So if you want to do a whole bunch of different maneuvers as needed over a 20-year lifespan of a satellite, you're probably not going to want to do a whole bunch of little small solid fuel boosters embedded all over your satellite, because you'll have to fire one off each time you want to do something. So rather probably want to use a liquid or a gas fuel for that kind of thing, something that has a valve that you can shut off or on as needed. So anyway, nice. Okay, now that we've covered all of rocket science,
Delta V.
Yeah, fundamentally, that is the thing it is called the rocket equation because it underpins so much of what rocket science is. Fundamentally, rocketry is getting a chunk of mass from here to there. And there is often space. And so how much do I need to do that? Well, I have to overcome Earth's gravity, and I have to get up to enough speed that it will stay in an orbit, and that, again, see our intro to orbital dynamics. The thing that keeps you in a specific orbital band is that you are moving fast enough. If you slow down, you're eventually going to deorbit and pile into Earth. And so you need to be moving at a specific velocity to stay in an orbital band. That means that you have to keep that velocity going. You have to attain it in the first place. All of that means delta V requirements.
How do you not melt your metal?
Well, that's an issue, and it was an issue in early rockets. Basically, in the early days of modern rocketry, think the 30s, 40s, 50s, one of the great limiters in the different fuels was the temperature at which it burned at, because you would melt your tanks. You didn't have some of the advanced materials that could withstand high, really, really high temperature combustion. And so fuels that potentially had really nice specific impulse just weren't practical because you would burn through your tank. Material science, which I don't think we've done a podcast on, but maybe we should. Basics of material science. Yeah. Anyway, advances in material science have yielded different materials that are better able to withstand those high temperatures and the pressures that come with them. But yeah, that's absolutely a factor. If you, and this goes into rocket design, some of those high temperature resistant materials might be kind of heavy. If they're heavy, that's more mass. More mass means you need more delta V to get that. Well, you don't need more delta V. You need more fuel to achieve sufficient delta V to get that giant chunk of heat resistant mass into orbit. You could build your fuel tank out of aluminum. You could build it out of spider webs and dreams. But then it might melt, and then all your delta V doesn't matter as your rocket burns through, and then what's the term that NASA used? I think it was rapid unscheduled disassembly. That's what happens.
Blowing up.
So,
all right.
Yeah.
Rapid,
anyway,
unscheduled. Yes, that's wonderful.
People make things up.
Okay,
it's
right. You got to make it more. When you're getting paid as much as some of these scientists, and your rocket blows up, you probably better have a technical term for it.
Yep.
Okay.
There's more parts to the rocket equation, and we can go into more or less of it. All right. So, based on all of that, what questions do you have about rockets and rocketry and rocket science?
Okay. Yes, I have questions. I saw for the first time in my life, I think, the other night. I live in Southern California. I saw what I think was a SpaceX satellite or rocket, whatever. I saw it launched from, I assume, the Air Force Base is at Vandenberg or whatever up north here in Southern California.
Yeah.
I saw a launch, and I have questions because two things I didn't expect to see. Well, at least two, maybe three. One was at the top of the, the rocket thingy. There's
rocket thingy.
Yeah, well, you know what I mean. There's like is the word penumbra? Like there's it's got lines coming off of it on either side.
Oh, yeah, that kind of shroud of colorful magic dust.
That's what it is. Pixie dust.
Yeah, it's basically the same stuff that they put in the airliners to make the chemtrails. See our basics of conspiracy theories.
I knew magic was real, and that's what I'm going to use to make my rocket.
Yep.
All
okay.
Right.
So, yeah, is your question, what is that stuff?
What is that? That's one question. Yeah.
Okay. So a rocket tends to be massive. It has mass. It has a lot of mass. And as it moves through the atmosphere, it displaces the air that is where the rocket now is, because mass cannot exist in two places at once, or rather, two chunks of mass cannot exist at the same time in the same place. Your rocket is shoving a whole load of air out of the way as it moves up, and that air bunches up in front of it, and you get shock effects, and you get all of those types of things. What you're seeing, I suspect, is just the distortions based on all of that air and all of the moisture in that air being violently buffeted out of the way. And it builds up just like the water in front of a ship builds up. The wave, the bow wave of a ship, does not start at the metal, it starts some distance in front of the ship. As water touching the ship pushes water in front of it, which pushes water in front of that. Same with the air in front of a rocket. There is a propagation of disturbance, and you get those effects. And it's cool and it's pretty.
It was cool.
And
I
it
liked
keeps the populace sedate. Conspiracy.
Most
theories.
importantly, yes.
Yes.
Okay. That's good to know. Okay, then the other things that I did not
I
expect.
guess I should say that's what I'm assuming it is. I don't actually know. I haven't looked it up.
I mean, it sounds.
If any of
very
our
likely.
listeners out there actually know why those phenomena are visible and it's not what I just said, leave us a comment on one of our social media things, and then audition to take over as a presenter, and Carl will put you on the show maybe.
That's right. For a small fee. Okay. The other things that I saw from this rocket, one was the angle. I actually, I was coaching a softball team of 12-year-old girls, and one of them even asked me, she said, why isn't it going up? Because it looked like it was kind of headed southeast. Like it was, of course, going up, but it had kind of an arc to it.
Mm-hmm.
And it looked like it disappeared kind of in the southeastern quadrant of the sky.
Yep.
Is that just our angle at it? Is it just headed straight up, or does a particular launch angle in order to achieve a particular orbit?
Yeah. Well, okay. So because the Earth happens to be round, and not round like a pizza, but round like a beach ball, this is one of the things that drives the flat earthers nuts, because if the Earth was flat, yes, it would go straight up until it hovers in the firmament, suspended by the dark space magic or whatever.
Not dark space.
If you go back to our Basics of Orbital Mechanics podcast, I gave an analogy about a cannon on a mountaintop. And if you think about a large mountain sticking up thousands of feet in the air, and a supervillain living there, and he has his cannon that he's going to shoot at the world's cities and hold them for ransom and whatever. Okay, I won't go into his story, but you have a cannon up there. The cannon is going to fire a projectile horizontally with a certain amount of propellant, and the projectile, therefore, moving at a certain speed. And as it flies out there, gravity is going to pull that projectile down to the Earth until it smacks into Des Moines or something. And unless you pay because all the mountains around Des Moines, unless you pay the supervillain's ransom.
Okay. Yeah.
So, what if you add more propellant to get that projectile to move at a faster speed? Your mountain is in Wyoming. Now the shell is not going to hit Des Moines, it's going to reach all the way out to Nashville before it plonks into the ground. Now, what if you put even more propellant so that you could fire the shell such that it would reach all the way across the Atlantic and hit Barcelona? I mean, you'd be a war criminal or something.
I was going to say, you just started the war with Spain.
So let's go. Now, what you may notice is that Barcelona is not super close to Des Moines or Wyoming. In fact, because of the curvature of the Earth, it's a significant distance, a significant portion of a circle around the Earth. What if you put enough propellant in there such that the the shell was moving so fast that by the time gravity pulled it a certain distance downward toward the center of the Earth, the curvature of the Earth had actually made the ground curve away from your shell by the same amount? Your shell would be falling towards the Earth forever and never hit the ground because it would be falling at the same rate that the ground is curved away from. And that is ultimately what you have with orbit. And that's what you were observing. You saw that rocket go off, not necessarily up, but at a angle leaning towards the horizontal. It was zipping off south, and it was getting up to that speed thanks to the delta V being applied to it. It was getting up to a velocity where the Earth was going to curve away from it at the same rate, or even faster than it was falling back towards the Earth. So that's what you were observing there, observing literally that supervillain cannon in action.
SpaceX is a super villain.
Well, that was probably launched from Vandenberg Air Force Base, so make whatever inferences you will there and be careful about it.
I won't make any inferences, I know. Okay, good to know. Okay, last question then about what I saw. The other thing I saw, and this is something I know that layman is also familiar with, is these rockets often have stages.
Okay, yeah, let's talk about that.
Because I saw one, kind of, pull, like part of it fell to the ground, and like kind of a firework looking thingy, and the other part was headed off. Yeah.
Yeah. Well, going back to the rocket equation, the whole delta V thing, a lot of that and how much delta V you can get out of it depends on your mass ratio, right? Well, as your fuel burns, and given that your rocket is mostly fuel tank, you're going to end up, as your fuel burns, with a bunch of empty fuel tank kind of just hanging there, being mass that is no longer super useful because the fuel has burned out of it. But it's still attached to your rocket, so you have to lug it around with you, and it throws off it maintains a less optimal mass ratio. But what if you could kick part of that fuel tank off of your rocket as the fuel burned off? That is more or less what staging buys you. You burn off your initial chunk of fuel to get out of the atmosphere. The fuel is gone out of a portion of the rocket. Let's get rid of that portion of the rocket so that our next burn of fuel can be wholly devoted to moving the remaining chunk of rocket and fuel and stuff that we have up to that higher velocity. Basically, staging just makes your rocket a little bit more efficient. Now, it's super efficient if you reuse those stages, which is what SpaceX has been doing of late, and that's kind of cool. That's how they keep it is part of how they keep their launch costs as low as they are, because they now have usable rockets. At the same time, they're able to get big chunks of payload into orbit more efficiently because they're not payload. They're not lugging an entire Falcon 9 orbit. That's what you have when your rocket is going up in orbit. You're not boosting the whole rocket into orbit. You're boosting about a third of the rocket into orbit, really the upper stages. And the first stage, which is generally huge and around 2/3 of your total mass, that splashes down in the ocean somewhere. Sometimes you recover it on a ship. Sometimes it just it goes away. But regardless, because you don't have to lug it into orbit, you can have a vehicle.
Right.
This is why staging. Any further questions?
No. Well, okay. Wait, do I have another question? I feel like I have one more, but Cameron, did you have a question?
Now, once again, I have answered all of the questions about rocketry and science.
It's
Correct.
not so much a
No more-
question that I have now, but I did have. I thought it was really interesting that rockets are actually locked to the ground till the thrust is at its maximum before it's released.
Yep.
I thought that was
The
interesting.
reason they do that is to make sure that the thing is actually going to work.
Doesn't have spontaneous disassembly or whatever.
Rapid unscheduled disassembly. Because
Right.
if something is going to go wrong in your rocket, you really don't want. Basically, if you have it clamped down, and something goes wrong, you can abort. If you don't have it clamped down and something goes wrong, well, your rocket is probably flopping its way into the air, possibly out of control, and then it, lands in the parking lot when it fails.
Then it becomes like
not
those.
Wholly making that up.
So
I bet you're not.
safety.
Yeah, go ahead. Ken.
Safety.
Now,
That's
there's a
what we're
couple
going
parts about that. A solid fuel rocket motor or a solidly fueled rocket, you don't really clamp that the same way because once you light that thing, it's going. Liquid fueled rocket that you can shut off, yeah, that one you would clamp down. You do actually, any rocket, you're going to bolt to the launch pad before you light it off so that it doesn't tip over, because that's also terrible.
Right.
But even with a solid fuel rocket, when you light it off, you're going to trigger something that's going to shear off all those restraining bolts and going to allow the vehicle to go. But yeah, once it's lit, it's not stopping. The liquid fuel rocket motor, clamp it on, make sure that the thrust is nominal, which only takes, that happens very quickly. You release the clamps and it moves.
Okay, I had one other question, and then I'm going to read a comment on one of our podcasts from a user, because I figured this is a nice way to include our, did I say user? It's because I'm a software engineer. Listener. Okay, last question though.
Like
We talked about staging. Our staging, it seems like based on what you described with staging, that it's possible that the different stages of the rocket would have different fuel types because the elements of your equation have changed.
Yes, they absolutely can, and they often do. If not solid versus liquid, then often different compositions of liquid. Once you're out of the atmosphere, you have to worry a little bit less about some of the different types of concerns. But the other thing is you'll often have a main booster with a main fuel type. The Delta 4 is a good example. It uses a combination of liquid oxygen and liquid hydrogen, and its exhaust is water, which is cool. But next to that, you can strap on a whole bunch of small solid fuel boosters that give it some extra thrust. So you have that mixture of solid and liquid in the same vehicle. And it's just, and the space shuttle was kind of the same way. The space shuttle, the vessel itself, the shuttle part, used liquid fueled engines. That was what was in that giant tank. Oh, I'm sorry, that's a bad example because the entire thing was liquid fueled. I apologize. But yes, you do have vehicles that use different types of liquids, or occasionally you'll find solid liquid mixtures, things like that. Yeah, that's the thing.
Okay, cool. All right. So is that well? Let me read a comment, and then we can wrap up the complete anthology of rocket science. Okay, so this is a listener whose username is Hannah Salem. Hanasalem. Honestly, I don't know. But he or she said, I actually really enjoyed this. I love that it said actually, as in like they were going into the podcast assuming they weren't going to enjoy it.
I mean, that's how I approach this.
I was going to say that's the way most of us. Okay, I actually really enjoyed this. This is, by the way, about the basics of trigonometry, which does sound kind of like maybe you wouldn't enjoy it too much. But it says, I really enjoyed this. I'm a year 7 student, and this podcast shows me how to use trigonometry in real life. I know how to use it, but learning why you use it in real life is helpful. So.
Well, thank you, Hannah.
Yeah.
Now you know how to use rocketry in real life.
I don't know how to use trigonometry.
Go back and listen.
Yeah. Okay. One other. I wanted to share one other podcast comment. This is from Fern and O, and this is on the Basics of Mechanical Engineering podcast. And it's very informative to hear someone touch on examples of situations and projects I will potentially face as an engineer in the near future. Great podcast. So, got some feedback. I'm not going to read the negative ones because nobody wants that. No, I
posted negative ones
every once in a while, but
so sad. It's okay.
Yeah, who needs that negativity? Positive. On the positive note, Tasmania and Northwest Territories still listening into the podcast. So
that's that. There we go.
Yeah.
Love those Tasmanians.
Yeah, exactly. Okay, Matt. Any wrap up final words on basics of rocket science? I think we've learned a fair amount here.
Final words on rocket science? Yeah, it's great.
Yes.
Now that you know it, you can apply it in your daily lives somehow.
Yeah, I shoot rockets off frequently.
Yeah. But, I mean, we hear this all the time. It's not rocket science. Well, rocket science actually isn't all that complex. Rocket science is figuring out how much mass you have to get moving how fast based on how hot something can burn.
Yeah.
The end. Okay, it's a little bit more than that.
I was going to say.
It really does. So many parts of rocket science come down to that equation. I have a thing that I want to put up into orbit. It has a certain mass. Based on that, I need to have a rocket that also has a certain mass. And based on that, it's going to have X% that's fuel and Y% that's everything else. And that fuel has an efficiency rating of whatever it is that makes this whole equation work. And if any of those parameters change, then you know how you need to change everything else to get your thing into orbit.
Nice.
Rocket Science 101.
Delta V.
Delta V.
So let's say I was a super rich person whose name rhymes with Belong Tusk. And I want to.
Then you have my sympathies and a bunch of other emotions.
Put my car that I created into space. About approximately, how much would you say that would cost?
Well, a bunch of mass. The payload there is a car's worth of mass. That means that based on the rocket equation, you're going to need a vehicle that has enough fuel such that it can apply the delta V required to heft that car into space. That's going to be a ton of fuel. But you can do it, especially if you understand the rocket equation. You can absolutely make it happen, and it has happened. Now, you need a ton of fuel to do it. You need a ton of mass. You need relatively efficient fuel. And you need structures that can support that whole endeavor. But it can absolutely be done, and it has been done. So, and you use the rocket equation to figure out how best to do it.
Right.
Are space elevators ever going to be a thing to take
That's
away rocketry?
not rocketry, and also, no. There's way too much stuff that will go wrong.
All right. Well, my takeaway from the podcast is
nothing can be taken away from this podcast. It is perfect.
No,
Oh.
yes, I think I learned a fair amount, but the pixie dust that surrounds rockets is, I think, my main
That's what I
takeaway point.
want. Chemtrails needs to be the takeaway from rocket science. This is why I can't have fun anymore.
That's right. Yeah. You just okay. No, this the knowledge mat, as is all of our listeners, thousands of people out there listening to the podcast. Go ahead and share it with friends, and we have just to tease. We've got a biotech podcast coming later this month.
The basics of becoming a cyborg.
That's correct. We have a biotech engineer doctorate coming on. We get the best guests, and we have the best hosts. So and Cameron's back and dropping the knowledge, and Matt is on when he feels it appropriate. So
there we go. I do have some knowledge.
Well, thank you.
I'm excited
You
to
do,
learn
absolutely.
about organic computers.
Organic computers. It'll be a good time. Okay. Well, thank you, everyone, and we'll see you guys next podcast.